Hello, everyone. Welcome to the April 14th edition of Math 262. Reminder that you have WebAssign due on Friday. Um, I want you guys to know that we are almost at the end of the semester, so you can make it. I believe in you. Today and tomorrow, we're going to be talking about conic sections. So, what is a conic section? Well, a conic section you might have seen back in high school. So if you did, that's great. But if not, we want to make sure we're all on the same page. It's the intersection of a plane with a double, what they call double napped cone. That means like a cone and a cone stuck together. So I'm going to show you what these look like. There are 7 types of conic sections. The first 4 you're probably very familiar with. They are the circle, the parabola, the ellipse, and the hyperbola. And you can see from this picture how the different conic sections are formed, how they intersect a plane with this cone where you have 2 cones on top of each other. These are the degenerate conic sections. These are the conic sections where the plane passes through the point where the 2 cones intersect. So you see you can get a point, a line, or 2 intersecting lines. These are what are called the degenerate conic sections. So when the plane passes through the vertex, the resulting figure is a degenerate conic section. All right, and they're called degenerate because they are, you can define them via simpler ways. There are multiple ways to view conic sections. So this is the geometric visual way of understanding them, but some people prefer algebraic equations. So the conic sections are the solution sets So you take an equation like this. You set equal to 0, and you find all the x and y values that make this equal to 0. Now, sometimes you get one of the 7 types of conic sections we saw above. And I don't know if you did this in your pre-calculus class, but when I was in pre-calculus in high school, we had to take these general equations and then find the conic sections and graph them. It was this long process. Okay, there's one more approach to conic sections, and the third approach is to define the conic section as a locus. A locus is a collection of points satisfying a particular geometric property. For example, a circle is the collection of points xy equidistant from the center HK. And from this, you get the generic equation, or the standard equation of the circle, which is h minus x squared plus y minus k squared equals r squared, where r is the radius. So now you've seen all of the ways that we're going to use to describe conic sections, and we're going to go through the different conic sections we presented previously. So the first conic section we're going to talk about is the parabola. So what is a parabola? Well, let's first talk about it from this locus of points definition. A parabola is the set of all points that are equidistant from a fixed line, which we call the directrix, and a point called the focus. Okay, and the focus is not on the line. The midpoint between the directrix and the focus is called the vertex. And the line passing through the focus and the vertex is called the axis. Okay, and a parabola is symmetric with respect to its axis. So let's take a look at this picture. So here is a picture illustrating all of the parts of the parabola that we just talked about. You see we have a line for the directrix, and we have the focus, and each point of the parabola is the same distance from the focus as it is from the directrix. And that's where you see D1 and D1. You see the distance from the focus to a point on the parabola and the distance from the directrix to a point on the parabola. And then you see similarly for D2. The vertex you see is right in the middle between the focus and the directrix, and the axis runs through those 2 points. So from this, we can create the standard form or equation of the parabola. So the standard form of the equation of a parabola with vertex HK and directrix y equals k minus p is x minus h squared equals 4p y minus k. So if we go back to our picture of the parabola, we observe that p is the distance between the vertex and the focus. Similarly, p is the distance between the vertex and the directrix. Okay. And similarly, for a directrix that's vertical, the equation is y minus k squared equals 4p x minus h. So, as I said before, the focus lies p units from the vertex. The coordinates of the focus are h, k plus p. That's for the first scenario. And h plus p, comma k. That's the focus for the second form of the parabola. The first one is a parabola that opens up vertically. The second one's for a parabola that opens up horizontally. So we're not going to prove all of the formulas that are involved in the parabola. However, I think it is nice to understand why these formulas are true. So I'm going to go through a little bit of a proof today, because I think that it's important that you as mathematicians understand, how do I prove such things? Sometimes it's easy, sometimes it's just algebra, but sometimes it's more difficult. And being able to do this is a very good skill. So let's look at the case where the vertex is hk and the directrix is y equals k minus p. Okay, so observe that the focus must be at h k plus p. So let's draw a picture and see why this is true. Let's say here's our vertex at the point h k. That means our parabola opens up something like this. And here is our directrix, y equals k minus p. So this distance right here is p. Here's the focus. So we know that the focus must be the same distance from the vertex as the directrix. And so that means the focus must have a y coordinate that is p units above k. All right, excellent. So we know. So let's pick a point x, y. We know that the distance from the focus to the point is x minus h squared plus y minus k minus p squared. Okay, and technically we take the square root. The distance I've just described is the distance right here. And the question is, what's the distance to the directrix? Well, we see that that distance, the x value doesn't change. This is a point x right here, and the y value is just k minus p. So that tells us is that the distance from the directrix to the point is the square root of x minus x squared, which is just 0, plus y minus k minus p squared. All right, so let's solve this equation, see what happens. So we set these two things equal to each other because we know that the distance between the line, that's the directrix, and the point must be the same as the distance between the point and the focus. So square both sides, And now it's time for algebra. So let's expand this piece right here and this piece right here. And what this tells us is this is x minus h squared. And if you don't know how to expand these kinds of things quickly, you will learn. And this should equal the expansion right here, which is y squared minus 2ky plus 2yp minus 2kp plus k squared plus p squared. And you see that a lot cancels out. These two terms on the left cancel out with the right. This cancels out with this, and this cancels out with this. So I believe what you are left with is x minus h squared should equal 4yp minus 4kp, which is 4py minus k, which is exactly the equation that we said should be true for the parabola. So this is the equation of the parabola. And we were able to do so with just a little bit of algebra. Okay, so let's look at a problem that might involve some calculus, because that's the name of this class. So let's say we have a parabola defined by an equation, y equals 1/4 x squared minus x. How can I find the vertex? All right, well, I want you to think about what this looks like from calculus. We know this parabola should look something like this. So I want you to try to find the vertex, and I'll show you how to do it. Well, what do we know about parabola? The vertex is at the bottom, so therefore the derivative is 0. So if we take the derivative, we get 1/2 x minus 1. We set this equal to 0. And then we plug this back in to our equation to tell us that y is 1/4 times 2 squared minus 2. So our vertex is at 2, -1. That's the calculus way of doing the problem. What's another way? What's something else we can do? Well, let's say we want to find the directrix and the focus. How do I find the directrix and focus? Well, I can put the equation of the parabola back into the standard form. So remember, the standard form looks like x minus h squared is 4p y minus k, where hk is the vertex. So let's do that for our equation. Now that we know that the vertex is at 2, -1. And the equation of my parabola is y is 1/4 x squared minus x. So what we must do is we must complete the square. So this is equal to 1/4 x squared minus 4x. And we're going to add 4 and subtract 4. So this tells me that y is 1/4 x squared minus 4x plus 4 minus 1. Okay, so that's 1/4 x minus 2 squared minus 1. So let's move everything to the other side. It says that y minus 1 is 1/4 x minus 2 squared. excuse me, y plus 1. And this tells me that 4 times y plus 1 is x minus 2 squared. You see that this is 4 times y minus a minus 1 is x minus 2 squared. So you see that the 2 and the minus 1 are coming from the equation of the vertex. So let me write one last thing. This is telling me that 4 times 1 times y minus a minus 1 is x minus 2 squared. That tells me that this is P, this was H, and this was K. So remember, the directrix has equation y equals K minus P, and the focus has coordinates H, K plus P. Well, that means the directrix is y equals K, which is minus 1, minus P, which is 1, y equals negative 2, and the focus is H, which is 2, K, which is negative 1, and P, which is 1. So it's at 2, 0. All right. So let's go to Desmos. And let's type in the equation. Here is our directrix. Here is our focus. And our parabola is right here. And so what you can see is, if I annotate it, this distance is 1, and this distance is 1. This distance is 2, and this distance is 2. This distance is 2, and this distance is 2. So this is the directrix. That's the focus right here, that blue point, and this point right here is the vertex. All right, so let's go back to our page and give you guys an example to work. So now it's your turn. This one's going to be a horizontal parabola. I want you to find the vertex, focus, and directrix of the parabola y squared plus 6y plus 8x plus 25 is 0. All right. So let's talk a bit about parabolas, because they're actually used in real life a lot. So we're going to talk briefly about what a surface being reflective is. So in physics, a reflective surface is one where the tangent line at any point makes equal angles with an incoming ray and the resulting outgoing ray. Okay, so let's take a look at a little picture and see what that looks like for us. So let's trace a little path of light. Let's say that the light is traveling here. Let me annotate this. And then it goes outward. And here is the tangent line. This would be the outgoing ray. That was the incoming ray. This is what we call the angle of incidence. And this is what we call the angle of reflection. So these are the physical concepts. And what we find out is that a parabola is a reflective surface. So you might not know that, but any ray that goes through the focus, here's the focus, will make, when it hits the parabola, will have an angle of incidence and angle of reflection that are the same. Conversely, any light that hits the surface of the parabola horizontally in this picture will go through the focus. So what is this for? Well, there's two things that we use this for. If you have a, let's say, a flashlight, you put the light bulb at the focus of the parabola, and then all the light that is emitted from the light bulb will go out in the same direction, horizontally in this picture. What that does, it will have all the light focused in a single direction, as opposed to having the light go in many directions. That's the principle behind a flashlight. The other thing, which is sometimes used in solar furnaces, is you take a parabolic reflector and the light comes into it and it's all focused at the focus of the parabola, and you can use it to melt metals. Similarly, this is the principle behind a telescope or reflecting telescope. All the light comes into the parabola, which is the mirror, and the mirror then reflects it and focuses it all at the focus. Hence why it's called the focus. So this leads us to what's called the reflective property of a parabola. So let P be a point on a parabola. The tangent line to the parabola at P makes equal angles with the following two lines. The line passing through P and the focus. The line passing through P parallel to the axis. Okay. So we could prove this property, but it's not very very fun to prove. It's actually pretty easy once you learn vectors in Calc 3. So you should really ask Dr. Gladden to show you this property using the dot product of vectors in the fall semester. All right. So today we're also going to introduce the ellipse, and we'll finish it up next time. But there are some properties of the ellipse that I think you will find relatively easy. So why do we care about the ellipse? Well, it turns out that planetary motion goes in the shape of ellipses and not circles. However, in our system, most of the planets follow elliptical orbits that are pretty close to circles. So anyway, here's what an ellipse is. An ellipse is the set of all points the sum of whose distances from two distinct fixed points called foci is constant. We say foci because it's Latin. Let's see. The line through the foci intersects the ellipse at 2 points, which we call the vertices. And the chord joining vertices is the major axis. And its midpoint is called the center. And lastly, the chord perpendicular to the major axis at the center is called the minor axis. Okay, so that's a lot of words. Let's take a look at what these actually are. So remember, an ellipse has 2 points called foci, or one focus here, one focus there, and D1 is the distance from one focus to the point, D2 is the distance from the other focus to the point, D1 plus D2 is a constant. That is how we define an ellipse. And you can draw an ellipse by taking a piece of string, you have 2 thumbtacks, and then you put the pencil wherever you draw the line taut, and then wherever that little crook in the string is, you draw a point and you can drag that around and then draw the ellipse using string and pencil. Here is the description of the ellipse. You can see where the 2 foci are. The major axis goes through them. The center is at HK. The vertices are the points on the ellipse that are on the major axis, and the minor axis, which is shorter than the major axis, goes through the center and is perpendicular to the major axis. So we see there's a lot of terms going on here, but it's a really nice picture. So we can define the standard form of the ellipse. We're not going to prove this one. It's not as easy as the parabola, but it is possible. The standard form of the equation of an ellipse with center HK and major and minor axes of length 2a and 2b respectively, where a is bigger than b, is we have one of two possible forms. The foci lie on the major axis. C units from the center, where C is equal to C squared is A squared minus B squared. Okay, so let's do an example where we can graph everything and see that this all matches up. So let's look at the ellipse x squared over 1 squared plus y squared over 6 over 4 squared is 1. So we observe that A is 4 and B is 1. This tells us that C squared is A squared minus B squared is 15. It tells us that C is root 15. We see here that the center is 0, 0. That's easy. And that tells us that, this tells us that the major axis is vertical. And that tells us that the foci are at root, 0 root 15 and 0 root, negative 0, 0 comma negative root 15. And the vertices are 0 comma 4 and 0 comma negative 4. So let's take a look at this on Desmos. So let's graph our equation. Here's our ellipse. We see the center is pretty clearly at 0, 0. We have one vertex and another vertex. And then we have our foci. And you see the foci are very, very close to the vertices here. That's because this ellipse is very spread out. All right, now I'm going to have you try one. There's an example for you. So I want you to find center, foci, and the vertices of the ellipse x minus 3 squared over 16 plus y minus 1 squared over 9 equals 1. So go ahead and work that in notes. Let me know if you have any questions, and I will see you all soon.